Right, there is a mathematical construct called radial unit vector. We use this mathematical object a lot in some physical situations. So as a result, I would like to spend a separate time on explaining what that thing is. Okay, so so there's no physics involved in here, so it's just a purely mathematical topic. So we have a reference frame, which means that I have an origin in here, and the XYZ axes, and I would like to basically I consider another point in here in that space. So we usually express the points by its Cartesian coordinates. So this x, y, z are also the components of the position vector. In any case, consider the vector drawn. Let's just call this as the vector in here, right? Let's just consider this vector. So we just call this as the position vector. So that's the position vector for point P, let's say. So we know that in terms of this, the Cartesian coordinates, the position vector is given like that. In any case, forget about the vector, and then let's talk about its magnitude this time. So the magnitude is basically the magnitude of that position vector is the distance of the origin from that point. So that's essentially called the radial coordinate. Of the same point P. So these x, y, z are the Cartesian coordinates of the point P, but there are also other kinds of coordinates that we use to describe the same point, and these are not Cartesian coordinates. So the radial coordinate is one. So later in physics, you are going to see, for example, things called spherical coordinates. I'll just draw it in here as an example. So spherical coordinates of point P, for example. In that case, we use that distance and two angles to describe the location of the point. So as a result, if that's the point and r is that distance, theta is the angle with the z-axis, and then the phi is the angle of the projection of that point on the xy plane. There's a point in here, this angle in here. In any case, so basically this is just an alternative set of three numbers that shows the precise location of that point. So these are spherical coordinates, and the radial coordinate is just one of them. Okay, so we're not going to use spherical coordinates in here. We don't need the angle variables, but in some problems of spherical symmetry, for example, we are going to use this radial coordinate, and that's that one in here, right? So it is that radial coordinate. So you can think of it as a coordinate like the Cartesian coordinates, but it's not Cartesian. In any case, so let me choose a different color in here. We can also define a direction, a unit vector associated with that coordinate, and that's always defined as the direction in which that coordinate increases. So basically, it is that direction in here. So this r hat is the unit vector like that. So r hat, this is called the radial unit vector. So this is the unit vector along the direction in which the radial coordinate increases. So in that respect, this is quite similar to the Cartesian unit vectors, like the I unit vector. And I have said that some people just call this as the X unit vector because it's associated with this Cartesian coordinate. So we have another coordinate in here and a unit vector associated with that coordinate. So in both cases, the unit vector is pointing along the direction in which the coordinate is increasing. Okay, so that's the similarity in here. So that similarity is important. But there is a small difference in here. So for the case of this point, for example, the Cartesian unit vector x hat, for example, is going to be along the same direction no matter at which place the point is. Okay, so that's the important property of the Cartesian unit vectors. But the radial unit vector is going to depend on the direction of the radial unit vector is going to depend on where the point is. So if I choose the point like that, in that case, the radial unit vector would be pointing like that. So if my point is in here, then the radial unit vector would be like that. So that's a slight complicating factor for the radial unit vectors, but it's just like the other coordinate unit vectors, apart from that distinction. But that's something that's going to be important. In any case, so as a result, you can see that this r unit vector is along the same direction as the position vector. So as a result, we can write down the r unit vector as the position vector divided by its magnitude. Basically, the position vector divided by its radial distance. So you can write this thing down as like, I don't know, in unit vector notation, in terms of the Cartesian components. You can write it down like this. Right, etc. So I'm not going to say anything further about this. So, but there's one example that I need to give. So let me change the colors. Why do we need this? Because if I have a point charge at the origin, so this is the time where I'm just going to use this physical example. So for electric fields, of course, we are going to need this notion. So I have a single point charge at the origin, and I would like to find the electric field at the location of P. So I just draw this line that connects the origin to the point to the origin. So let me try to draw this a little bit correctly. So R is that distance, and I know that if the charge is positive, then there's an electric field in the radially outward direction. But if the charge is negative, then the electric field is along the radially inward direction. Okay, sometimes we would like to, for example, think about the sign of the charge and then as a result decide on the direction of the electric field. But however, if I'm using the radial unit vector, in that case, I don't need to do this. So basically, I need to write down the electric field as some kind of a number multiplied with the radial unit vector. So in each case, I can write down the electric field like that. But we see that when the charge is positive, this number in front is positive. It's a positive scalar. And if the charge is negative, the number in front is a negative number. So in here, we know that we can write down this electric field like that. This is charge divided by r squared multiplied with the r unit vector. Okay, so as a result, this formula is a correct vector expression that gives the electric field vector at this point, whatever the sign of the charge is. Okay, so in any case, the number in here is actually like the components of a vector. So this number in here is called the radial component of basically the vector E, right? It's just like the x and y components, the Cartesian components, except that, of course, we have the radial unit vector in here. So because of this, sometimes we also write down the subscript r in here. Instead of writing E, we just say ER in here to actually stress on the fact that this is the radial component. Just like in the, just remember that in the case of for example, the Cartesian components, I'm just going to write down two components in here. Yeah, let me also write down the third. So basically, the x component is multiplied with the corresponding unit vector. So this is a similar kind of a notation. So the vector is basically the radial component multiplied with the radial unit vector, and the vector has no other components, right? So that's the simplifying factor. Okay, so as a result, this is the radial component, and usually when we are expressing the electric field in here, we don't write down the vector quantities in this way, but we just simply write down the component in here. So in that case, I will usually write this thing down as E, but formally I should write this thing down as the radial component of the electric field. That's simply given as 1 over 4 pi epsilon 0 Q divided by R squared. Again, I'm going to repeat this. If the charge is positive, that means that the radial component is positive. This corresponds to a situation where the electric field is pointing radially outward, meaning that the electric field vector is parallel to the radial unit vector. Otherwise, if the charge is negative, in which case the electric field vector is pointing in a direction of radially inward direction, which corresponds to the fact that the electric field vector is anti-parallel to the radial unit vector, or we say that the radial component of the electric field is negative in that case. Okay, so understanding that relationship is very important, because usually instead of using this notation, I'm going to use the component notation.